All right, folks, in this part of the video, we're going to talk about the applying the rules for derivatives of trig inverses. We went over that in the previous one. That's labeled part 1, and now we're on to part 2. So let's take a look at this first example where it says take the derivative of the sine inverse of x squared. And yes, indeedy, we do need to use, the old chain rule here, because we've got more than one parent function cooking here. We've got a sine inverse and an x squared. So let's go through how I would do this. You're just going to apply the formula that we learned in the previous video, which is going to be 1 over the square root of 1 minus your u, which in this case is x squared. And then you take whatever that u is and square it off. And then lastly, you multiply by the derivative of this guy right here. Well, the derivative of this, clearly 2x. So we're going to multiply by 2x. And now it's just a little light cleanup on aisle 2 here, as we have 2x all over the square root of 1 minus x to the 4th. And there is really nothing more you can do about that or should want to do about that. So we'll stop right there and call it good. All right, so what I want you to do is pause the video and try it at the bottom of the screen. Try it on your own. No, really, pause the video. I'm serious. Be back in a moment. And we're back live, and as you can see, I've committed the vile acts of calculus. Following the formula, 1 over the square root of 1 minus our u raised to the second power, and then times the derivative of our u function, which is 8x squared, and just a touch of simplification later, 16x over the square root of 1 minus 64x fourth. All right, let's move on to the next example. The dreaded secant inverse. Not what we wanted to hear or see, but that's the way it goes. So we're going to follow the formula here, and it's going to end up being, let's see if we get this right, 1 over absolute value of our u function, and then times the square root of our u function, which is 5x to the 4th. We need to square that off, and then take away 1. And lastly, we need to multiply by our derivative, which is, of course, 20x to the 3rd. Okay, now something interesting shakes out with this particular problem. And I want you to take a peek at the absolute value part of this thing. Before we start cleaning up, I can tell you we can safely drop the bars here. Anytime you take something raised to the 4th power, you're going to get something positive. And when you multiply that by something that's guaranteed to be positive, like a 5, the final result should be positive. So I don't see any reason why we can't drop the bars if it's a positive power. And let me back off of this here and say that we need to get our 20x to the 3rd in the numerator. Okay, and then squaring this off, this is 25x to the 8th minus 1 inside the radical. Now, remembering we can't touch anything inside the radical, but we certainly can cut those down by a common factor of 5, and we could probably get rid of 3 powers of the x thanks to this thing called cancellation. We can reduce this down to 4 over x times 25x 8th minus 1, all inside the radical, and there you go. Okay, now remember, before you just willy-nilly drop the bars, you have to look and see if it's going to be positive before you can make that jump. Now, if you can't get rid of the bars, then you can't do any of this in red with the cancellation. That would be a no, no, no. Don't do that. All right, so this one is an example of what we just talked about. Same situation here. The thing is, I can't guarantee that 3x minus 4 is always going to be positive. So the derivative here is going to be 1 over 3x minus 4. And then inside, we've got 3x minus 4 raised to the 2nd power minus 1. And then multiply by the derivative of 3x minus 4, which is 3. Okay, now again, like we just said, no guarantee that this is always positive, especially for secant. So therefore, I'm just going to have to let it go. And there, I did it again. I forgot to move my piece from the side up top here. I forgot to move that 3 up there. One of these days, I'm going to get better at that. Okay, now what about the inside here? Can we foil? Is it going to serve any purpose? No, not really. It's probably not going to serve any necessary purpose. So I think it's okay to just leave it alone and call it good. Now again, if you had another task that followed this up, then you might consider that particular task. I don't like this problem at all. I really don't. The way that this is written, somebody ought to be prosecuted in number 1. So this is going to be cosine inverse. I would write that as t root 2 because I really don't like the idea of this t being out here to the right because I'm afraid that I'm going to think it's part of the square root when in reality it's not. All right, so let's apply the formula for cosine inverse, and as we know, it is exactly the same as the one for sine inverse, except for the fact that it's not going to be negative, or it is going to be negative rather. It's just going to be the same thing, but -1 over the square root of 1 minus t root 2 quantity squared. Okay, now, what is the derivative of t root 2? Well, the variable drops out, leaving the constant. Now, believe it or not, that's a little bit to our advantage, as you will see in just a hot second here. All right, now down below here, I'm going to have 2t squared when I square it off. That's what I'm going to get in that little part of u squared. Now, folks, we need to, can we combine this? Well, we can, but it's not really absolutely vital. Oops, don't need the radical at that point. It's not vital to do it that way. In this case, it serves no purpose other than just to annoy us. So either one of those would be acceptable on the test. So just like everything else I've told you about with simplifying, if you think you're okay to simplify, no, you're probably not. So just don't try to reinvent the rules of algebra. All right, let's tackle one that's an arctan, and we're going to have the derivative as being 1 over 1 plus our u squared times our derivative, which is just going to be 3. And after a little mild cleanup, this is what we have. 3 over 1 plus 9x squared. And no, you can't simplify that any further. You can try, and I'll probably say that's not legal if you tried to do anything illegal, especially. All right, so what about this one? This one's kind of ugly because we've got a part we probably know how to do that's a little bit messy, and another part that requires, what does this require? Let me think. Oh, yeah. That requires the product rule. Okay, so here's my u and here's my v, and let's see if we can come up with something that's going to make sense here. So if I go to do the derivative of this thing, it's going to be a mess here. I've got u prime, which is the derivative of my little x there that's marked in green is 1, u prime times v, and then this is going to be plus my u times my v prime. Okay, well, what's the derivative of sine inverse? That's going to be 1 over the square root of 1 minus x squared. Okay, now you're probably thinking this is getting pretty nasty, and you're right. Let's take a look at what happens when I have to do this part right here, which is really 1 minus x squared to the 1/2 power. If I apply my power chain rule, then something really interesting shakes out on this one when you go to simplify it. Oh, that's going to be 2x. Good thing I caught it there. Okay, so here's what happens. This is kind of cool. The 2's cancel. These 2's cancel. This fella gets put downstairs. And all you have left upstairs when it's all said and done is an x, and don't forget that minus sign. So as we put this together and kind of simplify it, oh, well, that's happy news because these two now are exactly the same thing. And oh, by the way, they're being subtracted, resulting in 0. So the derivative is sine inverse of x. How convenient is that? Okay, not a bad plan here. All right, well, what about number 4? What can we do about number 4? Well, I'm going to recommend that we talk about something like this with the quotient rule. That might be the best thing to do. It's not exactly a good thing, but it could be worse. And I think you're going to find pretty fast that this gets super ugly in a hurry. Okay, so our low, which is sine inverse of 2x times the derivative of the high function, that's 0, minus high d low. Okay, the high function is 1, and d low works out to be 2 over the square root of 1 minus 4x quantity squared. And then this is all over a sine inverse of 2x raised to the second power. Okay, kids, don't combine the exponents because that wouldn't be legal. Okay, this is not being raised to a power of -1. This signifies inverse. It has a different meaning. So don't fall into that trap for the love of heaven and earth. Okay, and then when we clean this up after a couple of steps of algebra later, we're going to have something that is just ghastly to look at. And that's about all the further we could or should take this. A couple more examples here. Particle moves along an x-axis so that its position at any time t greater than or equal to 0 is that position function. What is the velocity? Well, hey now, we know how to do that. The derivative of position is velocity, so let's see what we can find out here on this particular situation. That's an x. Sorry, moving things around, but wanted to make sure I got the right variable here. X prime of t is going to be 1 over 1 plus root t quantity squared. And now I've got to do the derivative of square root of t. We've done this enough times to know that that's where it ends up. So a little bit of cleanup later. And now we can go ahead and try to find the velocity of the particle when t is 16. So if I wanted to find x prime of 16, which is ultimately what I'm trying to do here, 1 over 1 plus 16 times 1 over 2 roots of 16. Okay, that's 1 over 17. And then that's, well, that's going to be 2 times 4 for 8. And now I have to stop and think about this and try to figure out what 17 times 8 is. And you can tell that I'm probably stalling long enough to reach for a calculator and come up with 136. So 1 over 136, the velocity for that particular particle at t equals 16. Instantaneous velocity, of course. So if you got some trig identities or trig inverses that you need to figure out, then there are some ways around them. For the secant inverse, if you want to figure that out, well, its reciprocal is the cosine. So we'll take the cosine of the reciprocal, or cosine inverse of the reciprocal. And then for the cosecant inverse, then we'll take the sine inverse of the reciprocal to help us out. Now, cotangent's a little bit different because you have to do some shifting. because of the way the tangent and cotangent are related to each other. So that is the identity that you need to use to be able to find a calculator conversion. So these don't come up very often, but they're kind of nice to have. Okay, and now lastly, we've got the equation for a line tangent to the graph of cotangent of x at x is equal to -1. Well, you know, for the 48,000th time in this particular term, if I want to find the equation of a line tangent, clearly I need two things. I need a point, I need a slope. We know that the slope comes from the derivative. We'll get to that shortly, but we need to find the point. So what I need to do is I need to find the cotangent inverse of -1. Okay, well, what I might think about doing here is using that conversion identity. So pi over 2 minus the tan inverse of -1. All right, so the tan inverse of -1 is going to prove to be negative pi over 2. And that's because we're going to reach into the second quadrant. Go back to our first video where we talked about how to define the tangent inverse points. And actually, I goofed. That shouldn't be pi over 2. Shame on me. It should be pi over 4. So we're going to destroy that evidence and put pi over 4 there. Sorry about that. And then when you simplify that, you're going to get 3 pi over 4 as the ordered pair. So -1 and 3 pi over 4. All right, now for the slope, what we're going to have to do is we're going to have to come up with the slope, and that's the derivative. So y prime is going to be -1 over 1 plus x squared. And then the derivative of x is just 1, so no worries about that. And now I plug in -1, and ultimately this works out to be -1/2. So the equation of the tangent line is going to be y minus 3 pi over 4 is equal to -1/2 times x plus 1. And if you had to simplify that, you probably could, but it's not necessarily something that is probably top of our list. Okay, that takes care of our lesson on trig inverse derivatives.